as Chris said, I'm a scientist in the Team Science Core for ICTR, the Institute for Clinical and Translational Research. And one of the things that we're working on in ICTR is to help our scientists better leverage data science. And so it's a pleasure for me to introduce Finn. I've known of him for a very long time from previous positions with the department that I've held in the Department of Biostatistics and the Data Science Institute, where he now works. So Finn is a graduate of the UW-Madison Computer Sciences Department. He worked with Jude Shavlik, David Page, and Beth Burnside, the co-director of ICTR. So we've all known of him and his credentials for a while. And I just want to say how excited again we are to have him share his knowledge and expertise to help us all better leverage data science. And I think with that, Finn, if I left anything out, please jump on in, but I'm going to cede the floor to you. So thanks for joining us.
Sure. Yeah, perfect. Thanks for the intro. And speaking of things moving quickly and hard to keep up with, I realized that picture there, how much more gray there is in my beard now in just a year and a half. So things are moving. All right, I'm going to share my screen here. This one. Okay, there we go. Cool. Oh, you guys moved over there. So as Whitney said, I'm a staff data scientist at the University of Wisconsin-Madison in the Data Science Institute. I'll just put in a little plug actually at the beginning, I guess. The Data Science Institute, we're a non-departmental organization. We work with campus researchers at UW-Madison and really outside of UW-Madison as well. Researchers and like even companies too. We do like all sorts of data science research stuff. So lots of collaborative research things. And if you're interested in that, you can talk to me about that too. But yeah, so I'll just kick it off here. So I'm going to be introducing kind of like a little primer on data science for the non-data scientists right here. I put part one in there because I think the intent is to do sort of the intro primary type stuff in two parts, if I'm remembering that correctly. I believe I'll be speaking to you again in about a month. And then also just, please feel free to ask questions along the way. We want it to be like a little bit interactive. I do have two spots in the slides where I kind of want to open it up to the floor to ask people questions, but nothing too high pressure. So very, very, very low threat. Don't worry about it. All right, so when we're talking about a primer on data science, we should probably first try to define data science. And coming up with a specific definition of data science is perhaps a little bit tricky. I kind of like the graphic on the left. So basically, data science is the application of skills at the confluence of computer science, math and statistics, and then domain knowledge. I think, is a good way of just sort of like framing what it is just in general. And then those skill sets broadly include things like data engineering, model building, visualization and communication, and then problem solving. And we'll mostly today be talking about the data engineering and model building parts. But I'll just briefly go through each of these just to give you an idea, because I have little notes here. But so basically, like data engineering involves things like collecting data. So that sounds really simple, but basically it includes things like determining what needs to be collected to achieve our goals. Like we have a problem that we want to solve, so we have to know what are we going to collect to solve that problem, and then how should we even go about doing that. That might be complicated or it might not. Storing data. That includes figuring out how and where to store the data. So data needs to be in a format and a location where we can use it effectively to do something with it. Managing the data. That's like things like, what are the costs involved? How long do I need to store it? Does it change over time? Is it static? Who can and should have access to it? What happens when people leave? All those like logistical questions that go with managing data. And then also cleaning the data when we want to do actual analysis. So that's like, what else do we need to do to the data to do what we need to do? So like you ask questions like, is or are the data consistent? Do we need to do any sort of post hoc structuring or of unstructured to semi-structured data? Do we only need a subset of the data we have? And then in many cases, I'll just say you can expect the data engineering step to be the vast majority of your effort on a project. We joke, like often say like 95% of our job as data scientists is just like data engineering stuff. Excuse me. Sorry, recovering from a cold. It's like toddlers, am I right? And then, so the model building step is often seen as like the fun and exciting part. And it is also frequently the vast minority of the time that you spend on a project. So, the fun and exciting part is the smallest bit. But that includes things like, you should also speak about like exploratory data analysis. So you've already thought about and collected your data and put it somewhere, right? So now you're going to look at the data and just like generally get like summaries on it. You might look at summary statistics, you may look for like missing values, things like that, just basically to get an idea of, do you need to do some iterating on like cleaning or pre-processing your data? So you might go back to the data engineering step. Right, model fitting, that's often a fun part, right? So maybe there's some standard models, like maybe you're working in a particular, like a really well-studied area. And they're like standard models that you need to do with your data, and just like you've collected a different set, okay? Or maybe you want to try out some, machine learning algorithms and see what works for some predictive task that you're interested in. All sorts of stuff like that. And then evaluation. So you might be asking yourself, like, did your model succeed at predicting some outcome, or did some algorithm do better, or you did some standard model. Does it like compare with the standard of practice or the state of the art? Or perhaps you saw distributions or trends that you didn't expect, and those are interesting things to look at, right? There's typically a lot of room for like both art and science in the model building step, which is probably why it's fun and exciting. Visualization and communication, that should take a good amount of time too. Basically, you're just saying like you did some modeling, right? Like now you need to convey that to your particular audience. So you're just going to ask like, who's your audience? Are there standard figure types or things like that that they want to see when looking at their data? Are there subtleties to the findings that you uncovered, right? That require a more creative aspect of visualization. That's sometimes fun and interesting. And then really just the point is you need to work closely with your stakeholders to figure out how to visualize what you found in the model building step. And then finally, problem solving is when you're like clearly conveying those findings, right? So you visualize them, but now it's time to decide what to do with those findings. And again, you're going to be working really closely with stakeholders. As a data scientist, I should say, a lot of you are going to be stakeholders to data scientists, or you might be just dabbling in data science yourself. But the point is to get from the data science perspective, or data scientist perspective, this is what I would be doing. So then, do like the findings change the way that I look at a certain problem? Do I now have a tool that can improve standard of practice? Maybe that would be cool. Do I need to do more experimentation to answer my question? Do I need to collect more data? Stuff like, do I need to go just back to the data engineering step? There's all sorts of stuff, right? Like often you bounce between these things with most of your time spent in the data engineering step. But that's kind of the idea, is the problem solving part is working really closely with the domain experts, the really strong domain experts, and figuring out what we can decide about our findings there. And I guess like maybe that's the beauty of data science. I have a colleague who likes to say that data science isn't real. And it's just because it's like so many different things, right? But that's kind of the beauty, is it's just like it's a mix of technical and creative and interpersonal skills that you have to execute to achieve a common goal. So it's kind of exciting. Okay, so now that's data science in a nutshell. Everyone's going to be groaning probably at this, but let's talk about data just a little bit, right, in general. Like, what is or are data? Because it's important too. Like, and I guess we'll start out by just talking about measurements in data. And we can break measurements down into two broad categories. Typically, we would say categorical measurements and numerical measurements. And this is an easy thing to gloss over, but there's some pretty important subtleties that you need to consider when you're looking at measurements that you're collecting for some data set. Okay, and then categorical, we'll just talk about that first. Categorical measurements can typically be broken down into two categories as well. We'll usually say that they're the nominal and ordinal categories. Nominal values are just unordered sets of values like eye color, so brown, blue, gray, green, country, or like even binary yes, no type things. So those are encoded as just these unordered sets of possible values, right? And then ordinal values are similar, but they have an order, right, as it's in the name. So perhaps that could be like education level or a rank or something like that. Now, it's like kind of easy to just throw away this distinction, but it's actually kind of important. One reason that I'll note that it's important is that it's not uncommon to encode, say, nominal values as like an integer or something. So like for like efficiency in my data set, I might encode eye color as maybe brown is 1, blue is 2, gray is 3, and green is 4. But if we're not careful when we're modeling later, our model might then think like, oh, it's an ordinal value or it's a numerical value or something. So it might be like green is 3 more than brown, or like green is bigger than brown. Nope, it's not, right? So we have to be careful when we're thinking about the different ways that we've encoded data to even categorical data. So yeah, that's all there is for that. Then numerical, we also typically break into two groups. Again, kind of a subtle distinction here. So there's interval numerical data and ratio numerical data, and there are probably other types that I'm not thinking of, but whatever, interval and ratio. And interval things are like, those are types of numerical data where there isn't like a true zero value. There's not a none value per se. So that's like temperatures like measured in Celsius and Fahrenheit, because those have pretty arbitrary zero positions, right? And if you don't agree with me, think about it this way, right? So if you have, let's say it's Fahrenheit, right? It's 20 degrees Fahrenheit. Is 20 degrees Fahrenheit 2 times as warm as 10 degrees Fahrenheit? Might be easy to think so, but how many times warmer is 20 degrees Fahrenheit than 0 degrees Fahrenheit? How many times warmer is 20 degrees Fahrenheit than -7 degrees Fahrenheit? It just doesn't make sense, right? So like, but you can compute differences, but you can't compute ratios, basically, or proportions. And then there's ratio numerical data, and that might be temperature in Kelvin, because there is a true zero for Kelvin. And then you can actually just compute, the point is like these values, you can compute proportions and like multiples and things, right? So that'd be like height and age and so on. Yep, okay, that probably covers that. All right, so we've talked about measurements. Now let's take one level of abstraction up. So we'll talk about data sets as a whole. Typically, we'll break these down into structured and unstructured data sets. Most of us are probably familiar working with structured data sets. This is the spreadsheets and the databases of the world. And basically the point is, in structured data, you have data that has a predefined form with like rows and columns or fields. And then a row represents some fixed size set of measurements. And then each measurement has like a defined type, right? It's like numerical or it's categorical, for example, right? So then basically any single record in structured data will be the same length as others, and it'll have predefined sets of fields, right? And then unstructured data is things like, typically it's like things like images or video or text or audio, for example. And certainly like we can, as like a human, you can sort of like see it looks kind of structured, right? Like we can understand the data. But given a set of images, you might have, a lot of those images might have different dimensions, or they might be compressed using different algorithms. They could be colorful, they could be black and white. Maybe they have different contents that you care about. I'm seeing lots of messages in the chat. Should I be tracking those, or
No, don't worry
all
about
right.
it.
Oh, perfect. I won't worry. But again, if there's like a pressing question, feel free to unmute and like ask me. I'm happy to answer questions. But yeah, so the same can be said for like text data, right? If you have a whole bunch of text documents, they can have varying length. They're not all the same number of characters or words long. Some of them may be PDFs, some of them could be Word documents, some have figures, some don't. They may be in different languages, all sorts of considerations there, right? They're just not like apples to oranges necessarily. Or sorry, they're not apples to apples, they're apples to oranges instead of apples to apples, right? And then the same is said with audio, right? They could have different lengths, they might have different encodings, maybe they're mono or stereo, maybe some are with speech or other natural sounds, some are synthetic sounds, so on and so forth. And that's not to say that structured is easy and unstructured is hard. You frequently have a mix of these things. So anyone on the call, I assume several people work with electronic health record data. Sometimes EHRs include fields for like doctor's notes and things. So really that's, any time that there's like a text field that includes the user punching something in that they want, they could encode essentially the same information as someone else as in a different way. You're working with unstructured data. So like sometimes you might say that there's like semi-structured data, right? You have a structure and then you have some unstructured data in there. The point being, basically though, like there are different considerations we need to make when we're working with structured data versus unstructured data, right? So the way we model these things is, the models we choose at least to model them depends on the measurements and like the structure of the data. Okay, so that's data science and like just data at a high level, just the way to frame thinking about it, right? Everyone's probably thought about it this way before, but just want to make sure we're all on the same page. And then we will talk about data a little bit more. I sort of like did some prioritization of the things that I would talk about, but I figure now that we have like a common understanding of data, the way we're thinking about it, we might just touch on AI and machine learning a little bit now. So I'm going to do a brief like crash course on AI and ML. Basically, the point is like everyone's getting blasted from every direction on like new reports of some new AI or ML tool. But I think it's important that we're all on the same page of what that even means, and I don't think everyone fully understands what they are. I mean, I sometimes don't even feel like I fully understand what they are, and that was what my dissertation was on, like machine learning in biomedical applications. So, okay, so I think so we're at our first checkpoint where I want to like poll the group. I don't know how many people are here, probably plenty, but I'd like, if possible, for some brave souls to come off of mute and answer this question. Like, what do you think AI is? Like you're hearing about it in the news. Maybe you've read a ton of papers, or maybe you're like super well versed and you're just gonna preempt everything I'm gonna say. But would anyone be willing? I'm gonna stand here quietly. Would anyone be willing to come off mute and say how they define AI? I'm not gonna call names. I might, but I'm not gonna do it.
I see several. I'll call several names if no one steps forward here. So we'll give it another 30 seconds or so.
I guess I would define AI as a machine learning model. I think that's about just kind of it's a pretty broad, vague kind of definition. Just a machine learning model capable of accessing large databases to formulate an answer.
Okay, interesting. Yeah, so like more about like the model just using the data, basically. Yeah, so a model using data to answer questions. I think that's a reasonable answer, I think. Any other? Hopefully, I'm summarizing that correctly. Any other?
Vivek, do you want to unmute yourself and ask your question or say your statement?
That's a system or a model that defines or that can do things within a set of instructions.
So yeah, like so executing some particular set of instructions. Yeah, that makes sense to me too. I think so. To sort of spoil it, like I think what we're going to find is that there's like pretty broad definitions and whatever that will. I'll give it another moment if anyone else wants to jump in and.
I guess I think of it as encompassing all of the different tools, some of which are in development, some of which are already developed, that can generate information or knowledge beyond humans. Does that make sense?
Okay. So like like a knowledge extraction type tool would be like just in general. I think that's a reasonable definition too. And I think actually really, so I'll proceed now. I won't belabor this unless anyone really super wants to say their thing. I think all of those answers are fine and all of them fall under AI. And maybe the unfortunate thing about AI is that it is so broadly defined, or at least historically has been so broadly defined. So here's the definition that I'll give you, which is artificial intelligence is just intelligent behavior exhibited by computer systems. Okay, it's super broad, right? But that includes things like machine learning. One of you mentioned machine learning. That could include expert systems. That maybe gets at Vivek's answer. It could be things like path planning or game playing. There's like tons of stuff. And actually, excuse me, I really like actually Ray Kurzweil's definition from, I guess, 1990 at this point. But yeah, so the AI is the art of creating machines that perform functions that require intelligence when performed by people. I really like that one. I don't know. And it also falls into the spirit of like super broad definition. So let's just use an example to think about like what AI might be. So we're gonna go back, God help us all, 30 years in time to 1997, when Deep Blue, IBM's Deep Blue chess playing machine, beat the world chess champion Garry Kasparov. And so Deep Blue won. So they actually played 2 matches, but whatever. This is the second match when Deep Blue won the overall match of 6 games by 3.5 to 2.5. And then the question is, all right, so Deep Blue, this computer, beat Garry Kasparov. How did Deep Blue do it? It's actually not that complicated. So basically, Deep Blue was just a large system of handcrafted rules that determined like, at least this was part of it, that determined the value of any given board state. So that can be like you're looking at the board and you can think of things like how many pieces are on the board, how many of my pieces versus my opponent's pieces. Things like, do I still have my queen? Does my opponent have their queen? in like certain like fixed known positions. I'm not a chess guy really, but like, I know that there are like particular positions where people will analyze, from this position, you can do all sorts of stuff or whatever. So like things like that, right? Evaluating the value of a particular board state. And then it also had like super highly customized hardware that allowed it to search millions of possible moves every second. So from a given board state, it could search tons of moves ahead, making assumptions about like, how is my opponent going to move? So like I make this move, then my opponent probably does this, then I do this, then they do that, then I do this. And just like getting basically an average value down any branch of this search space and finding, your most optimal, like what's the best branch to go down of moves, right? And doing that every single step of the way. And then IBM actually even had the Grandmaster Joel Benjamin fine-tune the rules after watching it play for a while. So there was like additional fine-tuning through these rules. But basically the point is, this was an expert system of rules designed by chess experts, built on top of a relatively simple search algorithm, right? And just a lot of compute behind it. So the question is that AI? Does that count as AI? And I think, at least according to our really broad definition, absolutely it does. I think it's AI. And at the time, everyone certainly thought it was AI. But it sort of maybe suffers from this, like I think a lot of people now might say, oh, that's not AI, right? And it sort of suffers from this thing that's called the AI effect. Basically just like once AI gets good at something, it's like no longer considered AI, basically. I also, again, I'll just use a quote that I like from Nick Bostrom from 2006. It just says, a lot of cutting edge AI has filtered into general applications, often without being called AI, because once something becomes useful enough and common enough, it's not labeled AI anymore. And then, of course, there's the opposite effect where people will just call everything AI or whatever. Like that's a different problem. But the whole point is like, it's not, it's so broad, but it also has like a moving goalpost. So it's hard to really define it, but you can think of it as just like any system that like effectively exhibits intelligent behavior. Okay.
Hey, Finn,
I'm talking about that one. Yeah.
there's one question in the chat that asks if Deep Blue was a pattern recognizer.
So my gut reaction is to say it, not really, but I mean, kind of. So like usually when I think of pattern recognition, I think of like, we'll get to it actually shortly here, like unsupervised learning type tasks which I get. I mean, in a way, it's not like explicitly though. It's not explicitly built to recognize patterns, right? It's just it's explicitly built to, like, there might be some emergent behavior there that does that, like the evaluating the board state and then building that onto a search algorithm that just like goes down branches. So it's possible you could glean information that seem like patterns, but like Deep Blue itself isn't looking for particular patterns. It's just, I don't know. I mean, that's a hand wavy answer, like kind of, but not necessarily. But again, it's all kind of squishy. Like it depends on what you count as pattern recognition, right? It's evaluating a board state by just like counting pieces and so on and so forth, right? All these rules. There were like thousands of rules apparently that were built into Deep Blue. And there might be some effect of the system overall as like recognizing patterns, but it was never explicitly encoded to do so. That actually sort of touches on a point that I think I brought up with Chris and Whitney at one point, that I've appreciated over the years. As a computer scientist, I used to joke like computer science isn't a science because you have to put science in the name, which is whatever. That's a little bit flippant, but the whole point is like, as we build more and more complicated systems, computer science sort of becomes more of a natural science, because like we when we had really simple computers, we knew exactly what was going to happen from first principles because we built this thing. And now they're so complicated that like you could understand it from first principles bottom up, but at the same time they're so complicated that it's almost impossible to do that as a human. So you have to just observe and see what these systems do. So in a way, like that's sort of like touched that part in my brain when asking that question of like pattern recognition. But anyway, whatever. I'll move along. Hopefully that's a satisfactory answer. Or any other questions, burning questions that I should answer, Whitney?
Not in the chat right now.
Okay. All right. Cool. Let's just plow ahead then. Get to the exciting machine learning stuff then. So AI, just broadly intelligent behavior exhibited by computer systems, and then probably the most common thing. Someone I forget who mentioned machine learning specifically as AI in our little question session there. Machine learning is like subcategory of AI that is like, it's like the largest, most important subcategory of AI right now, basically. So like everything that you see that's called AI right now is probably, like in the news or whatever, is probably some machine learning system specifically. And so machine learning is the study of algorithms. I'll just read it from the slide here. They can learn from and make predictions on data. And usually those algorithms operate by building a model from examples in order to make predictions or decisions. So we'll talk specifically about 3 different categories of machine learning, and I'll exclude reinforcement learning. We can talk about that another time if people are super interested. Excuse me. So we'll talk about unsupervised, supervised, and semi-supervised learning. Unsupervised learning is when you have some input data, but you don't have any labels attached, and we'll talk about what that means in a minute, but you're just looking for patterns. So that's sort of like the pattern recognition stuff. Supervised learning is when you have a bunch of input data, but you also have labels attached to every single point of that data. And again, we'll talk about what that means exactly. But then what you're doing is you're building you're using an algorithm to look for a function that maps from data to labels, okay? And then semi-supervised learning is a mix of the two, where you have labels assigned to some data, and you have some data that doesn't have, like some subset of your data set that doesn't have labels, and you're trying to improve your supervised learning process by including both unlabeled and labeled data. Okay, so we're going to ground this. There's going to be like a little bit of mathy text on the left, but don't worry, but I'll explain it. It's actually really not complicated. All right, so we'll go back, we'll talk about data. We're going to use the terminology, an example is a single instance of some data that we collect. It's a specific object, and we'll call it X. So I'm going to use the example I like using is like, I'm walking through the forest and I found a mushroom, and I want to know, well, in the future, I might be interested in eating the mushroom, right? I don't know. I don't really like mushrooms, but whatever, I don't want to eat toxic mushrooms is the point. But so I'm just walking through the forest. I find a mushroom. That's an example of a mushroom, right? That's one specific object. And again, we'll call example X just because. Okay. And then you might hear this term. It might even be in that glossary that Chris mentioned before, this term feature vector. Basically, X is composed of a feature vector, which is just a set of measurements about that thing. So my mushroom, I could measure several things about the mushroom. I might measure its height, and I might measure its cap width, and I might measure its color and smell, and so on and so forth. But we'll just think of this as like a feature vector of 2 measurements for any one X. And I've put them here, right? We have a 2-dimensional space. We've measured the height of this mushroom that I grabbed. We measured the cap width of this mushroom. And then because I measured these 2 things about this mushroom, I can plot it in a 2-dimensional space. Okay, so that's where it is in that 2-dimensional space. I guess it's like, I don't know, 2.5 inches tall, and it's, I don't know, got a cap width of 1 inch or something. I don't know, roughly, right? So that's what I have that one mushroom. And then a sample is a collection of examples. So now I continued walking through the forest, and I picked 16, it looks like, 16, whatever. So 16 mushrooms. I found 16 mushrooms, and I measured their height and cap width of all of them. And now I have feature vectors for all of these examples, and I can plot them in this 2-dimensional space represented by height and cap width. Interesting. Okay, 16 mushrooms. Great. So that's where unsupervised learning comes in. If I just want to learn about the distributions of mushrooms that I found in my particular forest or whatever, I could use unsupervised learning, where the idea is I'm going to use some algorithm, and we're not going to talk about any specific algorithms. We can at some point, but to do clustering. So there are lots of algorithms that can do this, but basically it's like, looks like there are 2 groups here. We can obviously see that with our eye, but to make a computer do that, they're like specialized algorithms for that, right? And that's the heart of machine learning, is coming up with these algorithms that do this stuff. So, okay, great. We found that there are 2 clusters of mushrooms. They're probably related to each other in some way, we think, right? Cool. So that's unsupervised learning. Now going back to just our data, we have those same 16 mushrooms, but I have 2 more terms to introduce on the left there. So now I might attach a label to those mushrooms. So I took my 16 mushrooms home, and I might do some chemical tests or like animal tests to determine if they're toxic or non-toxic, which of these 16 mushrooms are edible, for example. So that's all the label is. It could be some discrete thing like toxic or edible, or it could be, if I have pictures or something, it might be, is there a cat or a dog or a zebra in the picture? Or it even could be like a real value thing, like maybe for these mushrooms, I'm trying to measure like some nutrient or some, I don't know what, right? But I measure some nutrient level in these mushrooms, and I want to see if cap width and, sorry, if height and cap width are related to that nutrient level or something. And then a training sample. So we had a sample, which is just a collection of examples. A training sample is a collection of example and label pairs. And so that's represented in my picture here by the blue and orange color. So I have the same 16, I assume you can see my cursor, but I have the same 16 mushrooms here. We'll just call the blue ones are the toxic ones and the orange ones are the edible ones. Okay, and I can just plot that as effectively a third dimension in color. Okay, so now we have supervised learning problem here. So if I want to grab a mushroom in the future and see if it's toxic or non-toxic, if I can eat it, I would need to build some classifier from the data that I've collected. And on the left there, the classifier is just a function that maps from the measurements of something, like the data that I've collected about the mushroom in this case, and it maps those measurements to the label that I also collected at some point, right? Meaning that in the future, if I walk back into my forest and I find another mushroom and I plot it in this height and cap width space, okay, it's kind of like by that line, that line being my classifier, where like edible ones tend to lie on the left, non-edible ones tend to lie on the right of the line. So now I have this new mushroom. Well, I have a classifier. We're going to say it's edible. Yeah, that's what I said, right? I think consistent. Right, so it's an orange mushroom now. Right. Okay, so that's the gist of supervised learning. And there are lots of algorithms that do that. Again, we can talk about those different types of algorithms that do that at some point.
So,
But then,
if you're going to get to this, I don't know if you're going to get to this, but I mean, given that's a deadly mushroom, how confident are you eating it when it's that close to the line?
That's a good question. Yeah, I mean, like that's an excellent question. That's like one of the key points of like machine learning, especially when you have like an algorithm that builds a classifier that's so easy to tell. Like clearly, my confidence is like defined by how far away from the boundary I am or something, right? Like, so here it's, yeah, like you said, it's really close to the line. I'm not going to eat the mushroom. Again, I'm not a big mushroom guy myself in general, so I'm probably not going to eat the mushroom anyway. But in particular, I'm not going to eat this mushroom because I'm probably only going to eat mushrooms that look exactly like the ones that I've measured before, if at all. But yeah, my sister's a big mushroom forager, but I'll commend her for it, no, too risky. And I guess I should say, like, maybe to speak to that a little bit more, there's like, that's like a whole area of study too, is like confidence and calibration and things like that. Like, how can you trust, or just like trustworthy AI or machine learning is like, how do you trust the answers that come out of these models? Some models are like super complicated, and like understanding why they gave some input data a certain label is almost impossible. Some of them are much more explainable. Yeah, maybe I'm not going to get into explainability or anything like that this talk, but that's certainly an interesting and like really deep area of study that's super important, especially in medical practice. Yeah. Anyway, so going back to the machine learning, the semi-supervised learning problem I said is when you have both labeled data and you have unlabeled data, and you're going to use the unlabeled data to try to improve, say, some supervised classifier. So I have that same line there. I have the same blue and orange dots, and so the classifier is just the previous classifier that I learned just from the blue and orange dots. But now I went back to the forest and I was like, well, I'm not going to spend the time and money to label these mushrooms, but I'm just going to collect another, I don't know, 20-ish mushrooms or whatever it is. And I'm just going to put them in there, and I'm going to try to use those to improve my classifier. So obviously this is a cartoon example, but it gets the idea across that by combining both labeled and unlabeled data, I can improve my model, because it's pretty clear I shouldn't be putting the line where it is, right? Like I think every human looking at this picture is like, obviously the line is there, or like, somewhere in between them, right? So really it adjusts my classifier to say like that same mushroom that I grabbed earlier, if I want to ask it, is it toxic or not? Now it's on the other side of the line, right? So now it's well, I guess now it's a toxic mushroom in my original definition of blue being toxic. But yeah, so yeah, wasn't super, like, maybe I'm confident enough now, Simon. I don't know. I don't know if I'm gonna eat that mushroom, but yeah, this sort of gets at that, and like it shows you that you can combine the two things and improve your performance. Okay. Yeah, go Chris. Any questions? We're gonna wrap up machine learning for now, and we're gonna just talk about data again.
Okay, so I do have a question, and if it's too specific or isn't going to contribute to the group's learning or to your, presentation, let me know. But when you did that mushroom thing, you picked height and width, as your two sort of main variables. What if those didn't have anything to do with what you wanted to know or
Right.
learn about mushrooms? And is that something that we hear about, like junk in and junk out, or what if you pick the wrong ones is what I'm saying.
Yeah, so I mean, that's where like sort of the combination of art and science comes in. I'll touch on it a little bit, I guess, in this section, but like it's a good question to ask. Like that's always like one of the most important things you want to think about when you're, say, at your data engineering step, right? Is like, so I have some problem I want to solve, and like that, whatever. That's a constructed example, but I think it's good at explaining some of these details. Like I need to decide at some point, like, one, what measurements are available to me to answer or to solve this problem that I want to solve? And are any of those useful? And if they're not, I probably shouldn't do it, right? Like, and maybe I can try or something and I might learn something, but that's maybe the goal then. Is not, the goal isn't to like predict something maybe, but just to be like, what can I find here? Like if I'm just like, that's like sort of like the heart of like data mining in general, maybe, I guess, is like knowledge extraction from data. That's such a broad term too. I'm sure people would yell at me for saying that, but super broad term. Yeah, I mean, I think I'll touch on that at the very end too, sort of just the question. I have like this one slide that's just like a bunch of questions to consider when you're working on some data science, like a predictive or decision-making problem. You just really have to think carefully about that. Like you can't just take, you have some spreadsheet that you got somewhere and you're not going to think about it at all, and you're going to throw it into a machine learning model and see what comes out the other end. It's like that's definitely way too risky and super in the realm of like garbage in, garbage out. Yeah, I don't know. I'm sort of belaboring the point, but yeah, it's like a really important consideration to make. Do you even have anything there that can answer the question that you're trying to answer? And totally, that might not be a good way of classifying mushrooms. I actually have no idea, but yeah. Cool. So we'll touch on that. I don't know if there are any other questions. People. I'll give like 5-10 seconds if there, or Whitney, if there were any questions in the chat that I missed. Anyone else want to ask some enlightening questions?
I don't see any in the chat, but people are welcome to jump in.
Good. We'll wait a moment. Going once. Okay, we're not even going to go twice. Right, so we'll get on some of these details, but yeah, again, feel free to jump in at any time. But to that point, sorry, I just realized we also have like a cut point here. I wanted to like take a moment and also force people to come off of mute to try to answer the question, is like, what makes data large? So we're going to talk about large data sets. Like for a while, there's like, the buzz term big data. And like people still use it. I think it's just, I guess, again, sort of spoilers. It's another changing, like the goalposts are always changing. So let's just think more generally, like what makes data large? Anyone have any? If you have a large data set, or you think your data set's large, why is it that you think it's large? You want to come off of mute and say that? Give their example.
When it crashes Excel.
I think that's a great answer, actually. Yeah, I like it.
I would say when it's too large to be able to think about in my head, I guess. Like when there's too many variables for me to keep track of, that I need something more than Excel and like a spreadsheet to look through.
Yeah, that's a good answer too. It might even crash Excel.
Yeah.
Or like a data set that's both very long and very wide. Like if you have multiple repeated measures on many patients over time.
Yep. Everyone's hitting on the themes that I'm already going to hit on, but whatever. Any other parting shots before we move on and basically just say what everyone already said? For the most part. Okay. Yeah, so these are the three ways I usually think. This is like the most common ways to think about it, I think, or like the most immediate ways that I think about it, is data in terms of height, width, or just overall space. So by height, I mean like this is like data where you have a lot of examples and not a lot of features measured. So not a lot of measurements about a lot of things. So tons and tons of mushrooms, but you only measured height and cap width. Okay, just thousands, millions of mushrooms. Width is when you have not too many examples, but you have a lot of features, a lot of measurements. So that's actually really common in like genetics data. So if you do like RNA sequencing or something like that, you might do that on 10, 20 tissue or cell samples or something, but then you have like 20,000 or tens of thousands of measurements about every single one of them. Problems come up there too. And then overall, just in terms of space that it takes up. And these are like the things that'll cause like Excel to crash often. But yeah, so there are lots of problems that come with just having like really lots of just really spacious data. It takes up a lot of space on disk. So we'll talk about them a little bit more specifically each. So tall data. So sure, okay, you have lots of examples, but you might not be able to capture the complexity of the problem being addressed. This gets back to Chris's question about like what if height and cap width aren't important to predicting toxicity? What if that's basically the types of problems that we're running into here. So so think of it this way, right? So I went back into the woods and I collected millions of mushrooms, and I only measured the height and cap width of all those mushrooms. And then I got the toxic and non-toxic label for all those mushrooms as well. Very possible, very likely even, that a bunch of those mushrooms are going to have very similar heights and cap width, but opposite labels. So maybe if I had collected smell or color or something like that, I'd be able to disambiguate that region of the data space to get at the answer of like what's toxic and non-toxic here. So that's sort of what we're saying, like when we say like, there's poor performance or generalization, you have a lot of data, but you don't have a lot of measurements about every single one of those data points. So you could keep measuring mushrooms height and cap width, but it's not necessarily going to answer your question of is it toxic or non-toxic any better by just getting more of them. And then there's also like increased potential for bias. So you can imagine like if you are doing like any sort of medical thing, right? Even if you have like a bazillion patients, but all you have is like demographic information or something, you're not necessarily going to be able to answer your question about drug efficacy or something like that, right? You got to measure more stuff in order to understand certain complex problems. So those are like usually the problems that come with tall data. It's not usually going to necessarily crash Excel. Unless it's like lots and lots, really, really, really tall data. It would have to be really tall. Wide data, this is again like the things like RNA sequencing, when you have a lot of features and not many examples. These are usually, they cause problems because like, right, so you have all these different measurements. Some of them could be collinear, like super correlated information. It'd be hard to tell like which things are important and which things aren't. And just when you have like more and more measurements, you have more opportunities for just like statistical anomalies. So more potential for spurious correlations within your data. And that might, that's not good for answering like a drug efficacy question or something like that, right? You don't want to be relying on spurious correlations for that. And then there's this general problem called the curse of dimensionality, where basically as the number of features grows, data points become sparse in the higher and higher dimensional space. As you keep adding features, you're increasing the size of the data space that they live in. And so the regions become sparse. So then your number of examples simply can't shed light on most regions of that information space then. So the way I like to describe it is like the number of features, the number of measurements that you made defines the size of the box. And then the number of examples determines how full that box is. And you want to balance between the size of the box and the fullness of the box in order to answer questions about it. Because if you've taken a bunch of examples and there's this giant, if like half your box has like no data in it, what can you say about that region of the box? Nothing, right? Or probably nothing. That's a philosophical question, but mostly nothing. Anyway. Okay, and then we'll call it heavy data. This is just data that takes up a lot of space on disk. Probably the biggest issue, this is the crashing Excel type problem. Although Excel, like, I think Excel crashes at like 10 megabytes sometimes, whatever. Right, so you have a lot of information, but heavy data can cause problems because it's just hard to move and to get it to where you want to do computation. That's particularly true if you have heavy data that's also like private data that needs to be like somewhere safe, right? If you need to get it somewhere to do some computation on it, not fun. And then fitting it into memory. So like a lot of algorithms will want to like, oh, load a data set into R or something like that and do something, right? All right, you have 6 terabytes of data or something like that. You're not going to load it into memory in R. You don't have 6 terabytes of RAM in your computer, I guarantee it. And then also just that sort of problem just leads to greater computational complexity. So you need to start thinking about strategies like, oh, I'm going to load chunks of my data at a time or something. So I need to come up with ways to do that efficiently. And then that might even be problematic because, like, maybe this chunk of data is correlated with this chunk of data, but I can only load this chunk at a time. And so there's all sorts of like weird computational issues that come up when you're talking about just lots and lots of data, especially when you're talking about like terabytes or petabytes or whatever. I've never run into that, but I've definitely run into terabytes of data. Okay. And then, so those are, I think, like the 3 main things that I usually think about immediately when I think about large data, like what makes data large. But then there's there's also like a few other considerations to make. Whenever you're working with large amounts of data, for some reason, people like to frame the issues that you run into as like the 3 or the 5 or the 7 or the whatever V's. I have no idea the origins of this, why it became a thing, but the V's of big data or large data are a thing. So in any case, we were mostly talking about volume. Previously, those 3 like tall, wide, and heavy data basically are volume problems. It's just the quantity of the data collected and stored. But then there's also like velocity of data. So this just speaks to like how fast data is generated or needs to be processed. I think most problems that most people run into are like batch problems. Like they have a snapshot of some database or something, and then they're just going to work with it and answer some questions. So the velocity is 0, right? It's not changing in any way. But you can imagine at the other extreme, there's like autonomous vehicles or something, right? Like they have cameras on the front and they have to classify objects in front of them and then make decisions from that, right? Is that a person or something? Should I be steering or braking or what have you? And they have to make those decisions, tens, hundreds of times a second. Totally different problem. You approach it totally differently from like batch processing, right? So that's a velocity thing. Variety, right? So you might have a mix of like free text or like structured records, images, all sorts of stuff in one big pot, and you want to have some model that like melds all of those things together. That's a particularly challenging problem, but that's like the type of problem you might run into. And actually, that's probably true of electronic health records as well, right? You have like free text, you have structured data, you might have like images associated with it, at least like maybe like x-rays or something. That's another problem. Veracity, right? So you're concerned with the reliability or the accuracy of the data. Just depending on that, you might choose different modeling methods depending on how much noise you think is in the data set or how like accurate you think the data set is. If your model, like the algorithm you use, is designed around the idea of being like there's 0 noise in the data, that can be super useful if you think there's a lot of noise in your data, right? And then value, which again gets back to Chris's question, like what's the potential usefulness of this data for making decisions or like gleaning insights, right? Like what I wrote down an example, right? So a person's favorite band or like color probably isn't going to be helpful in predicting the efficacy of some treatment. So probably don't need to ask that question when you're collecting your data. Okay, so I don't know. I encourage you all to look up there are more V's, more important V's. You can look them up. I'm sure people are coming up with new ones all the time. Lots of innovation in the V's for big data space. But yeah, oh, right. I'd forgotten about this section. Okay, so I'm just going to quickly go through a few, like, there are a bazillion different data formats. I'm just going to touch on a couple that you're probably going to run into, just because whatever, then you know, like, sort of what they are. First one being comma separated values or CSVs. This can also be like tab separated values, that's TSVs. You can use it, it's just a separator, it's just values that are separated by commas. This is your standard spreadsheet, and frequently this is like, you might get your data into like a CSV type format before you do final analysis. Really common to have CSV or like, that's sort of like a spreadsheet to be your final step before doing analysis. Nice thing about CSVs, they're human readable for the most part. They're easy to edit and manipulate, even like a text editor or an Excel or whatever. There's universal support for them, like any piece of software is probably going to be able to open a CSV. They are inefficient for storage though, because you're encoding everything as text. So even numbers that could be encoded more efficiently in binary would be text. Okay, whatever. They're not going to get huge, probably. JSON or JavaScript object notation, similar. It's human readable-ish. I have an example on the left there. There's some structure to it though. So I'll again, hoping people can see the cursor. I have like 2 patients here listed, Alice and Bob. And then Alice here has 2 visits. So there's some structure, like it's kind of like a database-y like format, but in a nested format. And one of the interesting things about JSON is that with CSVs, you have like fixed number of columns, right? But with JSON, you can actually have a little bit semi-structured data. So you can see here in Alice's visits, you know, each of them has a date and a blood pressure, but one of them has a fasting blood glucose measurement and the other one doesn't. Okay, that's interesting. So you can encode like a little bit further structure into the data. And there's broad support for JSONs. They're also inefficient for storage because they use text. You'll frequently see them like coming out of like web tools and stuff like that, or maybe like database dumps. Basically the same thing with XML, very similar, human readable-ish, broad support. Can include like maybe a little bit more structure. It can include like a schema, whereas JSON typically doesn't, and not by default at least, like not inherent to the definition of JSON. Also inefficient for storage, probably even more so because it's like much more verbose than JSON. Also probably comes out of like database dumps or often like web interface type things. So you might see XML files. SQL, you might get SQL files. So this is just like structured query language files. This is a database file, right? So someone might give you a .db file or a .sql file or something. These are nice because if you load them up into a database, they're queryable and they're easily modifiable if you need. They're highly structured, right? They have all these tables that are connected to each other. They're efficient typically because they're usually stored in like some sort of binary format. They have pretty broad support. Lots of tools can load up databases of different formats, but they're not like directly human readable unless you load them into a database and do a bunch of queries. Okay, might run into that. And then I just have one more here that you might run into. There are lots that you could possibly run into, but these are probably the most common. Then this one maybe a little less common, but hierarchical data format 5 or HDF5 files. They're like a container format that can contain all sorts of different data types. They're super efficient, like hierarchical structure and binary structure. They're pretty common in science. So like if you work with like physics data or like genetics data, sometimes you might get HDF5 type files. Anyway, usually very large and efficient for storing large amounts of data. They're not human readable and they require like a little extra software knowledge in order to use them in any sort of tools. Right, then with that, I'll move to my questions to consider. So I know we're running out of time. Hopefully we can have a couple minutes for questions to the group or from the group, but I'll just go through basically what we're getting to is at the end, like, all right, so you have a problem you want to solve in your clinical practice or something like that, right? Like, these are the things you should be thinking about. So one, obviously you just need to think about like, what's the problem I want to address? So given X information, say, I want Y. I want to predict something or I want to answer some question, right? Then you need to just answer, you know, like, how am I going to measure success? If I build a model to predict drug efficacy or something, how do I decide if I did it? Did I succeed, right? What measurements am I going to use? What's the baseline that you're comparing against, right? Like that's part of the measuring your success, right? Is there a standard of practice? Does your model need to beat that? And how would it beat that? How is the problem currently being addressed, basically? Do you need to collect data? Do you already have data? If you already have data, what's the format? How much do you have? Are there any restrictions? Where is it and where can it go? Like, can it get to a computer where it can actually, you can build a machine learning model or something like that, right? Or like, would an ML model even make sense here? And getting again back to Chris's question, do you even have the right measurements or labels to answer that question, why, from all the way up above? So you want to think about each of these really carefully. This is basically like data engineering step, right? But you want to think about all these questions. Basically, these are all the questions that we ask people when they come to the Data Science Institute and they're like, I want to do this thing. We go through all of these questions step by step. Like that's like one of the first things you need to do when you think about problems. Okay, we got 1 minute for questions. Sorry, Whitney, I dragged it out a little bit.